Howdy, howdy. I wanted to go back to our physics problems. The next chapter in the book deals with projectile motion, motion in a plane. But rather than just doing a simple problem or even embellishing the problem where we add in some nonlinearities that require numerical solutions, what I wanted to do is something a little more intermediate, maybe something between beginner and intermediate, where we have to optimize for a quantity that's within a system of differential equations. So what we're going to do is look at a projectile motion problem, baseball being hit by a batter, both with and without air friction, as I said, and we're going to calculate the distance the ball travels, and we're going to try to optimize to find the optimal angle at which to hit the ball relative to the horizontal to maximize the distance traveled. So again, as I said, we're going to be doing two things, or maybe better said than two things. We are going to do an optimization problem that our objective function is a system of differential equations. So with that, let's get on with it. So let's switch over to our notebook and zoom in a little bit. And the problem we're going to look at is this. So we're going to have a baseball player who hits a baseball of a known mass that's initially 1 meter above the ground when he hits it, and it leaves the bat initially at an angle of 30 degrees relative to the horizontal, and leaves the bat at 45 miles per hour, 45 meters per second, which is roughly 100 miles per hour. So there are two questions. Question one: how far does it travel in the horizontal direction before it hits the ground? And question two: if the batter has control over the angle at which the ball leaves the bat, relative to the horizontal, what's the optimum angle to maximize that horizontal distance traveled? Okay, and we're to do this initially in the absence of any sort of air resistance, and then we're to repeat that with air resistance where the drag force is given by this equation here. So it's minus c velocity times the absolute value of the velocity. So in other words, it points in the direction opposite of the velocity and has a magnitude of velocity squared proportional to the magnitude of the velocity squared, and we're given this proportionality constant of 0.001. So this is how we are going to go about solving this. We're going to set up a system of differential equations with event detection enabled, and then just solve these numerically. Now, we've done this before with the free fall parachute problem, so this should be pretty straightforward. For the second part, we are going to write a separate function that calculates the total distance traveled as a function of angle, and then we're going to use the SciPy's optimization abilities to actually maximize the distance traveled, calculate the angle such that the distance traveled is a maximum. And for part one here, with no air resistance, this can be done with pen and paper. And so we're going to work out what those equations are, and we're going to use Sympy to solve those equations analytically, and this will enable us to check our work. For the air resistance part, it's basically the same as steps 1 through 4, but there's no nice analytical solution, so we're just going to have to use numerical techniques. So, as always, we are going to need to import numpy as np. We're going to need some SciPy libraries here, and we're going to need to import the Sympy libraries. So from Sympy import star, and we're going to need the matplotlib as well. So import matplotlib.pyplot as plt, and then we're going to need to do the inline command. So matplotlib inline. Let's see if that runs. Looks good. Oh, nope, there's a problem. And it looks like I spelled pyplot wrong. Pyplot. There we go. Cool. Let's get on with it now. So off of the recording, I added this line here. This is just going to be to render the Sympy results in a LaTeX type of format, just to make it clear. Some of the results will be kind of ugly looking. I zoomed out to enter this text in, so let me zoom back in. Recall that our differential equation solver can only handle first order systems, and our equations of motion are going to come from Newton's second law, right? Force times acceleration is Force is equal to mass times acceleration, and acceleration is the second derivative of position with respect to time. So we just transform this into a system of first order differential equations. So our acceleration is going to be given by derivative of velocity with respect to time, and the derivative of position with respect to time is just the velocity. So we're going to have two first order coupled differential equations as opposed to a single second order differential equation. And in the x direction, our initial, obviously the velocity in the x direction is just the position derivative, and the velocity, the force in the x direction is 0 since we're not having any air resistance. So mass times dv sub x dt is equal to 0. Likewise, the velocity in the y direction is just the derivative of y with respect to time, and the force in the y direction is just the force due to gravity. Again, no air resistance. So for this simple system, the masses are just going to drop out, and we're just going to have four very simple differential equations to solve. Our initial conditions are given here. We're going to take the origin in the x direction to be 0. The initial velocity in the x direction is going to be equal to our total velocity vector, total velocity magnitude times the cosine of the theta, since it comes off the ground with a angle theta. So this horizontal component is going to have a component v cos theta, and in the vertical direction v sine theta. So in the y direction, the velocity, obviously I just said, is v sine theta, and the initial position we just took as 1 meter. So cool. Let's move on and code up the function that's going to handle these differential equations. So let's move down here. I'm going to create a function called NoDrag. If I could spell correctly, I would at least. Drag. It's going to take an argument t, and a variable, our dependent variable is going to be our capital X. And this function needs to return a vector of derivative, so I'm going to allocate that ahead of time. It's not strictly necessary, it's just something I do. I don't know why. Maybe it's a holdover from C days. So I'm going to create a variable called capital X prime, and that is going to equal zeros, and it's going to have length of 4. Length of 4, not r. I cannot type today. I mean, that's not nothing unusual, but yeah, so return x prime. Okay, so I am going to format things like this. The first component is going to be the x position, the second component the velocity in the x direction. Likewise, the third is going to be the position in the y direction and the velocity in the y direction. So I'm going to mimic this type of format up here. So now we can begin actually assembling this. So x prime 0, and that's going to equal, what is it going to equal? It is going to equal, that's our velocity in the x direction, but that is defined here as the first component of this vector x. So it's going to be x1. So x prime 2, or x prime 1, because it starts at 0. So that's the acceleration in the x direction, the derivative of velocity in the x direction. That's equal to 0. X prime 2, that's going to be the y position. So that is equal to what? That's equal to what? X prime 2 is the derivative of the y position. So that's the velocity. So that's x3, and x prime 3. That is equal to minus mg. The m's are all canceling out for this case, so I'm just going to put minus g. And since we haven't defined g, let's come up here and do that up here somewhere. G is equal to 9.8. So, good. That should be that. I don't know if this is going to take it. Yeah, we'll see if there are any issues when we actually run the code. Okay, my audio cut out for some reason in the middle of recording, so I have to go back and redo the events function. Not a big deal overall, since I wasn't that far ahead of here. So let's go
define events. It's going to take a variable t, another variable capital X, and we want this function to terminate when the y position is equal to 0. So y is our x2 variable, so we're just going to return x2. That should be that. And then we have to make this cut off the integration, so we're going to say events.terminal is equal to true. And we can also do events.direction just to make this a little more general. We'll set this equal to -1, and the negative means it will trigger this, it will terminate the integration or trigger an event when the variable in question is going from positive to negative. That's what the -1 means. If this were +1, it would be going from negative to positive. So for example, if you wanted to have like a model a rocket coming out from below ground, maybe you have the ground set to be 0. That initial, when it crosses that ground plane, you don't want it to trigger an event, but you do want to trigger an event when it hits its target. So this is actually pretty useful in real problems. Let's see if there are any errors here. That seems to run. What I'm going to do now, we're going to need to create a function called, I don't know what we'll call it, calculate range or something. But before we do that, let's just test, do a test integration and see if this actually runs. So let's come down here. We're going to need an initial velocity, so let's go v0 equals 45. Theta is equal to 30, and I'm just going to do np.radians. Theta equals np.radians theta. Okay, now let's need to set a time. So let's call I don't know. Let's call it TF for T final, and we're going to set that equal to 5 seconds. I actually don't know what the how long it'll take for the whole, before it hits the ground. So let's create our t-span variable. T-span is equal to 0 to TF. And let's do a t eval. That's going to be the times that it evaluates, the points that it gives us back. So let's do that as np.linspace. T-span 0. T-span 1, and I'm just going to pick 1,000 points. Any typos? No. Okay. So now we need to create a vector of initial conditions. So that's np.array. So our initial position in the x direction is going to be 0. Our initial velocity in the x direction is going to be v0 times np.cos theta. Our position in the y direction initially is 1, and our velocity in the y direction is v0 times sine theta. Okay, any typos? Apparently not. Let's go on now and set up the actual integration. So let's come down here and say solution is equal to solve initial value problem. Our function, I believe, was called NoDrag. Is that what I called it? Yes, it is. Okay. Now we need to put in what? I believe it's our initial conditions. Actually, it's the t-span, then our initial conditions, which I called capital X0, our t eval, and that's equal to t eval. And our events function is just called events, so I have to set events equal to events. Yeah, let's see if that actually runs. It seems to run. So let's print out that solution. Okay, it seems to actually be integrating. Success equals true. Here's all of our stuff. Do we actually get to an event? I don't know. Let's print out sol.t events. Yeah, so we hit the ground 4.6 seconds later. Let's actually plot this out just to make sure it looks okay. It should be a parabola if we plot the x position on the x-axis and the y on the y. So let's do that. So let me just comment that out for now. I think I'll delete it in a second, and we'll do, let's just do this. X is equal to solution dot y, and our x values are the 0th row, and I believe, yeah, I think it's the 0th row in all columns, and our y values are the solution dot y, and it is the 2nd row, all columns. That looks good. Let's go over here, plt.plot x comma y, and let's just make these, I don't know, let's just make these dots. Run. Yeah, that looks about correct. You see the shape is parabolic. We reach a maximum height of, I don't know, 20, call it 27 meters, and the total distance, the total range is a little over 175. So let's take this and we'll wrap it in a function, and it will just return this last data point here. So it'll give us this total distance traveled in the x direction. Actually, before doing that, let me just make one comment here. If we go back here and print out this t events thing, obviously this is going to give us the time that it hits the ground. But if we had not put this final time to 5, if we had done 2, you see that now t events is just an empty vector here, and we don't have a legitimate range. We just have the distance it travels in 2 seconds. So we have to make sure that it actually hits the ground first. So when we write this function, we're going to have to do a little bit of checking, and if it does not hit the ground, we're going to have to bump up this t final, and then perhaps bump up the number of data points in our t eval variable. So let's come up here where I've defined all my functions, and I'm going to create another function called calculate range no drag, and this is just going to take an argument theta, which will be our angle, initial angle in degrees. So right away we need to go theta is equal to np dot radians, and then theta. Okay, so now we can just cut and paste a lot of this stuff down here. So our initial velocity is 45. So v0 is equal to 45. Let's just delete that from here. We don't need this theta line. We can just copy and paste a lot of this here and put it up here. But let's make this, well, let's keep it 2 just to double check things. We'll bump it up to 5 in a second. And I want to make this n just so that the number of data points here that we return to be n. And then I'll define n as 1,000 up here. That case, we can bump up that number along with our final time if the need arises. So what do we need from down here? We're going to need our initial conditions. We're just going to need all of this essentially. So cut, paste. Here, what did I do? Oh, I'm used to VI, unfortunately, or fortunately, I don't know which. What else do we need? We don't need any of this stuff yet. But actually, let us take that. So our range will be, we'll call it we'll call the variable r, and instead of being the whole column of y values, it'll just be the last element, so the -1 element. And let's just clear all this stuff off of here and return r. So right now there's no error checking to make sure our events our event is actually being triggered, but let's just run this to test things. So let's go down here and we'll go print calculate range no drag 30. Okay, one error. What's going on? The function is not defined. Did I not run this cell up here? Run. There we go. Okay, so as we see here, there is no final event, no event detected, no event triggered. So let's take care of that right now. And this is not something I really did in my test code, so I'm going to do it here kind of live, and we're going to see how big of a train wreck this ends up being. So we're going to need to perhaps do a loop. So I want a variable called count, and that's initially equal to 1. And I'm going to have a variable called max count. I don't know. Let's just set it equal to 100. So let's come down here, and we're going to say while count is less than or equal to max count colon count is equal to count plus 1. We're going to need to indent all these. Okay. And actually, let's see. These are initially going to have to be outside of this loop. So we go up here, paste them in. Something went wrong. What the hell is going on here? Does that actually run? Okay. So far, so good. So now we're running this, and we're going to have to look at the events variable and see if that actually is not empty. Let's see. For debugging purposes, I'm going to keep that print statement, and so we're going to go if sol.t event. Why we can't spell all of a sudden t events? It is a list of vectors. So the first entry of there is the zeroth entry of the list, and we're going to look at the size of that. If that is greater than 0, this event exists. So we're just going to print. Let's just do this. Event exists, and print out the time. Okay. Else. And we're also going to have to break out of the loop here. Break. Else. Let us bump up the tf variable by, I don't know, 10%. So tf is equal to tf plus 0.1 times tf. And let's also bump up the variable n by the same percentage point. So n is equal to n plus 0.1 times n. That looks good. So let's see what happens if we actually run this. And let's just print out no events detected here. So print no events detected. Let's run that, and let's just call this function, see what happens. Okay, there's an error. Error. Spelling error, max count maybe. Where are we here? Max. Oops. There's an embarrassing typo. Max count. Still an issue. What did I do now? Max count. Max count. Oh, that needs to be a C. Still a problem. Oh, the TF. Dun, 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 dun. Oh. I don't know why these indentations are all getting screwed up. Okay, there needs to be a parenthesis here. That seems to work. Okay. Okay, there we go. So let's just bump this up to the initial TF here to 5 seconds, and let's just see if that runs. That does not. Variable R. I probably need to pull this out here, and this needs to go, let's see, up here. Let's see if that works. Okay, that works well. We don't need these print statements, so for the time being, I'm going to comment them out. And the range is not the second variable; it's the we want the x value, so that's the 0th variable, right? So how does that look? That's better. Okay, now let's move on to the optimization part of the problem. One potential issue we're going to have, it's a very minor issue, is that our functions in Sympy optimization routines calculate the minimum of some function, and we want the maximum. So what we're going to have to do is go here, and we're going to have to create another function. Let's just call it, hey, insert edit here. For some reason, the audio and video, the recording cut out in the middle of writing this part of the function here. What I was saying was that the Sympy minimize obviously calculates the minimum of a function. We were looking at we were looking for the maximum. So what we need to do is create a function here. I called it objective, and it returns the negative of the range. So finding the negative of a minimum is finding the maximum, and that's what we want to do. So we can actually minimize this function to find the maximum of this function up here. Back to the regular video. And another issue is because these depend on the cosine and sine of an angle, you can get multiple solutions, right? It's going to be periodic in 2 pi. So we're just going to put some bounds on our optimization, and those bounds are going to be between, let's just call it 0.1 degrees and 89.9 degrees. That should do it. We're going to need an equal sign. That does kind of help. Good. So now we go results is equal to minimize our function, which we just called objective. Did I spell that correctly? Objective. We need to pass in an initial guess, and I don't know, let's just call it, we'll just assume it, we'll just pick something at random, like 3 degrees. And I believe that needs to be a tuple, so let's just do this, 3 comma as a tuple, and bounds equal bounds. Does that run? There's an error somewhere. Objective not defined. I probably didn't run this. Run. And I think the issue is this needs to be a tuple of tuples, so let's put a comma in there. I think that's an issue. So run. Apparently not. Something else is going on here. Okay, I fixed it off camera or off of the recording. It took a while to track down. One issue was a slight typo, and the other issue was the fact that this thing passes in our initial guess as a tuple, and our function here attempts to make a modification of that original tuple. This NP radians thing assumes basically a float or an int or something. So what I did is I just pulled out the actual value of the angle with this 0 index. So now let's see, run. This runs. However, there is a secondary issue. So let's print out the results, and we get success is false. So we have an issue, and then we have an error message up here. And I have been Googling, and I cannot find the reason for this error. The issue is that it's not calculating the gradient properly, and is assuming we're going uphill when in fact we're going downhill. I've tried explicitly writing the gradient out numerically, to
write a function that calculates the gradient and passing it into the minimization function, but that hasn't worked yet, and I'm not quite sure what's going on. One way to get around this is just to change the algorithm. So we're going to do a method, and that's going to be equal to Nelder-Mead, the Nelder-Mead technique, Nelder-Mead algorithm. So if we run this, we get success equals true, and we get an angle of about 44.2 something degrees. That's reasonably close to the correct answer, but we can get a little better by giving a better starting guess. So let's just change this to 25 degrees. And now we get an angle of 44.9, which is a little better. The exact answer, I believe, comes out to be like 44.86. And one of the potential issues here is the way this calculates the exact cutoff point. Remember, it interpolates between the last two data points. So if we were to actually change this time step, let's make this 20, we get 44.83. So this is sensitive to that parameter. So we have to be a little bit careful here. For the time being, we're just going to ignore it and take that value as the correct one. So 44. Now, as I mentioned at the beginning here, for the case of NoDrag, we can actually solve these and solve for the range and then solve for the optimal angle exactly. So we don't have to use this numerical technique in this case. So let's actually do that. And because it's a little bit ugly, we will use the Sympy package to help us with the algebra. Before actually entering any more code in, I just wrote this up quickly. This is becoming a little long, and while this can all be done in Sympy, I'm just going to do a little bit here to speed things up. If there's interest in any further videos on Sympy, let me know, and we could do that. I wouldn't mind that myself because I'm not really that familiar with the package, and back in the day I used some symbolic algebra package called Maple to do some work. We had to evaluate some Taylor series of this really nasty expression, and we just use Maple to compute those. So anyways, back to this. If we have the x position as a function of time is equal to this, and if it travels distance r in that time, we could solve this equation for t. And in the y direction, we know that the final position is 0. It hits the ground, and it started at y0, and this equation gives the position as a function of time. So if we solve this for t, we can plug it in here, and we get a quadratic equation for the range of the baseball. So this is what we want to use Sympy to solve. We're going to solve for r to get a numerical answer. And then we're going to differentiate that expression r with dr d theta to get a derivative equation, set that equal to 0, and solve for the theta that maximizes r. So, okay, let's go. The first thing I'm going to do is this 1/2 g. I'm just going to enter this equation here as like 1/2 g over v squared. I'm just going to enter that as some constant. I'm going to call it a. Just so I don't have to type the whole thing out, and we can just evaluate this numerically. The next thing we need to do is define what symbols we're going to use. So we're going to do it like this. So we're going to use the symbols command, and we just have to basically list that all these are symbols. So it's y0, a, theta, and r. And this a is just going to be used for this term here. And I do need to put commas here. Comma a, theta, comma. Let's see, does this run? Cool. So now we're going to create our expression here, and I'm just going to copy and paste from my test code here. So we have an expression that's equal to the y0 here, tan theta, r tan theta, 1/2 this r squared. So we have this expression. Let's see if this runs. Okay, now we can just solve this for r. And we could do that just by using the solve command. Solve expr, and we want to solve it for r. So that seems to run. So let's print out R. Print R. So we have two expressions for R because this is a quadratic equation that has two solutions. So one is basically extrapolating backwards in time, which is not what we want to do. So we want the larger of these two. So what we could do if we really wanted to figure that out is just plug in numbers here and figure out which is the positive or the bigger range. I've already done that. And it is equal to the second term here, so I'm just going to grab that. So that should be like that, and I'm just going to, let's kind of look at this in a cleaner way. I should be able to type display and have it display like that. Yeah, cool. So that's our expression for the range. So what I want to do now is start to plug in the numbers for these things here. So I'm going to do r.subs, and it's going to take a list as an argument, and it's going to be a list of tuples. So the first one is going to be y0, and that is equal to 1. Our second one is going to be the capital letter A, which we are setting equal to lowercase a. And the last one, theta, that's equal to 30 degrees, and that needs to be changed into radians. So np.radians 30. Let's see if this evaluates. Yes, it does. And we get 180.66. So if we come back up here and we do a calculate range NoDrag, and we put in 30, that should give us basically the same answer. We need to print it, don't we? Do we need to print it? Why can't I find my cursor? Oh, there it is. Print. And let's also wrap this in a print. So there are two answers. The exact answer is about 180.66, and the numerical answer comes out to be about 180.22. So close enough. And now let's calculate the optimum theta. So let's go down here and create a variable called dr, and that's just going to be equal to diff r comma theta, which calculates the derivative of r with respect to theta. Let's display r, or display dr. So we get something that's kind of ugly there, but you know, we just plug in numbers, and that should be that should do it. And so we'll just create a variable called answer, and that'll be equal to solve dr with and we want theta, and the solve command will solve this expression here, dr, which is this, is equal to 0, and it's going to solve for theta. So that seems to be doing it. Let's print out our answers. What's going on here? Oh, there it goes. What's going on? Oh, I need to substitute in my my expressions. And let's cheat a bit by coming up here and just grabbing this statement that does the substitutions. Copy. We'll come down here. We'll paste it in, and we're going to say dr is equal to dr.substitute, and that should substitute in all of that stuff. So let's run that. And we don't need this theta because that's what we're trying to solve for. So let's get rid of this. So we get two answers here, and the one we want here is this one, this roughly 0.782 something. So let us just actually come up here and go ans is equal to ans 0. Okay, and now that needs to be turned into degrees. So I'm just going to come up here and multiply it by 180 and then divide it by np.pi. 44.86, which is about what we expected. And I think we're already over 40 minutes, so I'm going to split this video into two parts. So I'm going to call it quits here and see you in part 2.